Sound wave. Sound waves are composed of vibrating particles that collide with other particles and allowing them to vibrate and collide with more particles. When an object vibrates, it creates a pressure wave which produces sound. This pressure wave creates vibrational motion in the particles that can occur in different mediums such as air, water, or solid. There is no sound in vacuum or space, as sound can only travel through air, water, or solid medium. Objects will vibrate and travel through the medium first before they enter our eardrum. After hitting the eardrum, the sound will be interpreted in the nerve impulses, then to the brain. There are three categories of sound waves: audible wave, infrasonic wave, and ultrasonic wave. Audible wave. Sounds that occur in range of an audible wave can be heard by human ear. It is also called as sonic frequency, and frequency range of audible wave is between 20 Hz to 20 kHz. Example of audible wave are vibrating guitar, concert, and shouting. Infrasonic wave. Infrasonic wave is a sound wave that having frequencies below of the sound wave that detectable by human ear. Frequency range for infrasonic wave is less than 20 Hz. There are animals that can hear and communicate using infrasonic waves such as elephants, whales, hippos, and so on. There are two sources of infrasonic wave, which is natural sources and man-made sources. Examples of natural sources are volcanic eruption, ocean wave, waterfall, and earthquake. Examples of man-made sources are nuclear, chemical explosion, and machinery. More examples of infrasound are thunderstorm and jet engine. Application of infrasound. Monitor nature formation. Humans use it to monitor charting route and petroleum formation below the earth. Forecasting natural disaster. Humans use it to forecast earthquake, volcanic eruption, and clear air turbulence. Ultrasonic wave. Ultrasonic waves are sound waves that have greater frequency than those usually detectable by human ear. Frequency range for ultrasonic wave is greater than 20 kHz. Sound in this range are commonly used for communication and navigations by bats, dolphins, and some species. Examples of ultrasonic wave are dog whistling and underwater communication. Application of ultrasound. In medical, ultrasound machines emit ultrasound wave that echo back an image of a fetus or internal organ. In cleaning, ultrasound jewelry cleaners use sound waves that vibrate through the water to remove particles and dirt in jewelry. In shippers use ultrasound for navigations and locating objects underwater. Spherical sound wave. Spherical wave is when a point source emits sound wave uniformly in all directions. The sound power radiated in all directions is the same, and the speed of sound in all directions will be same too. A spherical sound wave propagates radially outward from the oscillating sphere. In most real-world situations, a wave originating at some sources does not move in a straight line but expands in a series of spherical waves. The basic mechanism for this propagation is known as Huygens principle, which states that any point on a wave is a source of spherical wave in its own right. For example, in this situation, there is a sound source in the mid-depth of the ocean that's shown as a white dot. The sound radiated equally in all directions, and the sound level is constant on spherical surfaces that surround the sound source. Sound levels decrease rapidly as sound spreads out from a sphere with a radius of r0 to a larger sphere with a radius of r. Next is the speed of sound wave. The speed of sound wave is the rate at which the disturbance is transmitted from particle to particle. The speed of sound depends enormously on the medium through which it travels. Sound travels at a constant speed and has frequency and wavelength properties. The speed of sound in the medium is defined by the rigidity or compressibility of gases and density of the medium. It has been proved in a form of the formula below. For sounds travel through gases, the speed is calculated using this formula. For sound that travels through air, speed is calculated using this formula. Referring to the formula above, the approximation is normally sufficient for dry air, but for greater accuracy, we must look at the more general relationship for sound speed in gases. If we tested the speed of sound in an oven, we will discover that this relationship does not work. The table beside shows that the speed of sound wave will be different when the sound travels in different medium.
Intensity of a sound wave is defined as the rate at which the energy is transferred per unit area, perpendicular to the direction of the wave.
What is the sound intensity that human ear can detect?
Human ear can detect the sound's intensity between the range of 1 × 10 to the power of -12 watt per meter square, which is the threshold of hearing, until 1 watt per meter square, which is the threshold of pain. Above of this range may cause pain to human. Have you ever witnessed an ambulance passed by when you stood on the side of the road? If yes, did you notice that the ambulance's sirens sound different when they are moving away? This is what we called Doppler effect. Doppler effect is the change in the apparent frequency of the sound depending on the relative motion of the source and observer. For example, when the ambulance at rest, both observer on the sidewalk will hear the same frequency. But, when the ambulance is moving, the boy hears a higher frequency of siren from the ambulance and shorter wavelength of sound as he is near to the source, while the girl hears a lower frequency of sound and longer wavelength as the ambulance moves farther away from her. Number 1 is receiver moving towards source. Number 2 is receiver moving away from source. Number 3 is source moving towards receiver. Number 4 is source moving away from the receiver. Case when the observer is moving. First, the observer moves with a speed of v0. Second, a point source is assumed remains stationary relative to the air. In the case where the person is moving and the ambulance is static, the frequency of siren heard by the observer will appear higher when the observer moves toward the source of siren from the ambulance. Next example is when the person is moving away from the source of frequency, which is the siren of ambulance. The frequency heard by the observer will appear lower when the observer moves away from the source of frequency. Case when the source is moving. First, when the source moves toward the observer, the wavelength appears shorter. Second, as the source moves away, the wavelength appears longer. For example, when the person is in static position while the source of frequency of the siren from the ambulance is moving. When the ambulance is moving toward the person, the apparent frequency heard is higher. Next example is when the source of frequency, which is siren from the ambulance, is moving away from the observer. The apparent frequency heard will appear lower.
What is the example of Doppler effect in our daily life?
Some example of Doppler effect in our daily life is sirens, police radar guns, pulse Doppler radar and audio applications. Police radar guns is used to keep a check on overspeeding vehicles. The radar speed gun will calculate the speed of object from which the waves have been bounced back from the transmitted radio wave signal. Doppler effect is used in audio applications to enhance the music quality. There are numerous plugins and effects that are based on Doppler effect. Do you know that Doppler effect was used to find missing MH370 flight? Doppler effect was used to determine the flight final path. Analysts identified slight changes in the frequency of the radio waves that the satellite received from the plane and deduced that the plane was traveling south away from the satellite at the equator. The plane's last paying was then deduced to be about 1,500 miles away from the coast of Australia. As conclusion, sound waves play a crucial role in our daily life because it is used by human and other creatures to perform various tasks. For example, in communication, ocean exploration, underground resources and hunting. Communication. People use sound waves to communicate verbally with each other. Our vocal cord generates sound waves that are transmitted through the air to the ears of listeners. Ocean exploration. Sound waves is applied in sonar devices that is used to explore ocean. Underground resources. Geologists use sound waves to search for resources such as oil under the earth. Hunting. Most of creatures use sound waves to hunt for food. For example, bats use a form of sonar to search for prey.